Hello everyone, welcome back to part 3 of lecture 2. So today we're going to go through the rest of the layers in the OSI model, starting with the transport layer, which is the fourth layer. Now, so transport layer takes information from the session layer and sends it off to the network layer on the sender side and vice versa on the receiver side, right? So this layer, this transport layer, is mainly responsible for the delivery of messages from one process to another. Now, what is this process? So on your computer, say you're texting on Facebook in one tab, you are on your browser, of course, and then there is a second tab which is using your YouTube. You're using your YouTube, and then on the third tab you're using Gmail, right? So these three tabs are three different processes. So each task you do on your computer is a process. So a computer typically runs thousands of processes simultaneously, always, all right? So this transport layer is responsible for identifying those processes, right? Delivering from one process to the destination process. Now, it might be within the same machine or different machines, but it doesn't concern on how the packet gets delivered. Its only concern is to identify which process is executing this request and which process to deliver this to, right? So say you are texting person A, so the transport layer would be like, I need to send this to text to person A, right? So yeah, something like that. Now in this layer, the PDU or the packet data unit is called segments. Although I refer everything by the name of packet, that is an informal name, but the formal name for the data packet in this layer is segments. Now this has a lot of functions, this layer. So the first one is the segmentation reassembly. Then there's adding port address and sequence number to the packets, connection control, flow and error control, and multiplexing. So we'll be going each one of them right now. So the very first function is the segmentation and reassembly of the data. So if we have a pictorial view, so there are three layers: session layer, transport layer, and network layer, right? So the white part is the segment layer. So we have a data here with the header, corresponding header of that layer, right? In this layer, this big data gets broken down into smaller packets. Now there are a few reasons. Some of them are like, the first one is it's always easier to carry the smaller data rather than the one big data, right? And it can avoid the single point of failure. For example, say you are downloading a file of 20 gigabytes, right? Now say this whole thing was a single unit. Now if even one bit of this whole file was to be corrupted, the whole file will get corrupted, right? It's not recoverable. You have to download that whole 20 gigabytes again. Now the advantage of having chunks or the segments is that if one segment is lost somehow or corrupted, it does not affect the other segments. Of course the whole file will not run, but you can always it's always better to download that small tiny segment rather than downloading the whole file, right? So I'm sure that most of you guys are familiar with torrents, right? So if you go there, you will see that there is something called pieces, right? So each piece is on its own, right? Something like that. Now, since the data is all segmented and whatnot, this data needs to be identified at the destination, because there is no ensuring that this data will be delivered sequentially. Maybe data 1 will go first, then data 3, and data 2 will be arriving at the last moment. So to avoid that, randomizing this data, they add a sequence number to each part. Like in the segments, in the transport layer, you see that I have marked them as D1, D2, and D3, right? So data 1, 2, 3. In the destination PC, it needs to arrive at the same, it needs to be ordered in the same way, right? So they add a sequence number. Now the transport layer knows how to get back this get these sequence numbers and put them in orderly fashion in the destination, which is called reassembly, right? So the last thing that you need to know is on this slide is that in the network layer, all these individual packets are sent to network layer, not like one big header. So all these headers you see, that h4 h4 h4, these are all copies of the same header. So even in the h3 they're the same, because this whole big data is going to the small chunks are all part of the huge bigger data, right? And all of this smaller data needs to go to the same destination in the same process in the same way, right? So all these headers just a copy of each other. Now I hope you're clear on that. And then we go to the next function, which is the identification of using port address. So As I said that your PC runs thousands of processes right now. We need a way to identify these processes in a very proper way, right? So what it does is it adds a ID, an unique ID to each of those processes. So if you want to check out, you can go to your resource monitor and just check there that under the network tab there is a whole list of processes, and beside each process there is a PID column which holds this port address. So transport layer basically assigns these port addresses and identifies the process that it needs to reach or the process that is executing it, right? So this port address is of 16-bit in length and is represented as one single decimal number. So there is a 16-bit number and we just convert it to one single decimal number. Like for example, there are some port addresses that are predefined, and say port 80 is used by the web, port 23 is used by the TCP. There are others that is used by DHCP, DNS and whatnot. All of them have fixed port numbers, right? All right, so now the next function is connection control. So TCP, if you haven't heard, there's a concept of TCP and UDP. We will be studying this in great length later. Now, TCP is a very secure way of communicating. So transport layer is also responsible for creating or establishing a very secure connection between the two end devices, a reliable and secure connection, right? Secure because it secures it, it encrypts the data and whatnot, it keeps it safe, and yeah, it creates a reliable connection. So why reliable? Because if there is a corrupted data, if there is a bit that's corrupted, it kind of has an error control as well, as we will see soon. So for connection control, what it does is it ensures that there is a communication between the two end devices. So at first they do a three-way handshake thing, like they establish a connection, like, hi, are you there? And the end device is like, yep, I'm here, I'm ready to accept your data. And only then will they start their communication between them, right? This is in the TCP. UTP doesn't do that, just for your information. So on the left side, there is the sender. On the right side, there is the receiver. So the sender is like, are you up? And the receiver is going to be yep. And when it gets the signal that the receiver is up, then it prepares its data 1 2 3 and starts sending. So first it sends 1, then 3, as you see, not 2, and then it sends 2, right? But in the receiving end, it again went back and in sequence 1 2 3, right? So that's how it's done. For the flow control, what it basically means is in flow control, the receiving and controls on how the flow of data is. Say, for example, you go to your friend's house, and usually the aunties in your friend's home, their moms, stuffs us with food, right? And at one point you're like, auntie, no more, I'm full, right? And that's the flow control, right? So say the sender is sending data, it keeps sending data, and the receiving end, there is a memory limit, right? So whenever its memory is full, it signals the sender that, wait, bro, don't send the data now, hold on. Then my memory is full, something like that. So if we were to see a representation, so it has 3 datas again. So it sends all 3, and at this point, its memory is full. So as you can see, at this point, this host has too many packets to process. Hence, the buffer to store incoming packet overflows, meaning it has no more space to handle the data. So at this point, if sender keeps on sending data, the receiver won't be able to receive it because there is no place to receive it, right? So at this point, the receiver sends a signal, so please send less packets. And at this time, the sender will wait for the next signal when the receiver can receive again. Finally, error control. So error control, the same concept. It will keep sending data. It sends one data. It sends a second data. And now the second data is lost, right? It's lost in transition. So the receiver did not receive the data too. Now, transport layer is smart enough to identify this. It says that it has 1, it has 3, but there is no 2, right? So what it will do is it will send a packet to the sender that please send packet 2, and then the computer will send the second packet again, and hence there is almost there's no corrupted data ever in TCP connections, right? So finally, multiplexing. So multiplexing is basically like a multiplexer, which you have learned in CSE421 digital logic design. It takes a lot of input and streams lines and out it. sorry, the output is one single type, right? So no matter what type of process you use, the fact that you stream videos, you text, you upload files, you play games and whatnot, all these processes are of different type and they all follow a different protocol, right? But in the very first lecture and even in the first part of this lecture, we discussed that there in communication there needs to be a fixed set of protocols that each need to follow, right? Now, transport layer, what it does is it converts all those very various processes into one single type that can be processed by the next layers. All right. So this is in the sender's end, and in the receiver's end, it works with the demultiplexer. So transport layer gets this one type of input and then it outstreams the various type of it kind of like decrypts all the type of processes into the types it were originally, right? So segmentation, this multiplexing and everything has a lot of advantages. Like segmentation allows session multiplexing. Multiple applications can use the same network at the same time, right? So it's not like if you use 3 applications, you need to buy 3 broadband lines. You have one single broadband line, but you are using everything simultaneously. Like you can text, mail, stream videos, play games all simultaneously, right? So yeah, multiplexing allows that. Then data segmentation facilitates data carriage by the lower network layers. So data segmentation actually helps that and it makes things more efficient, right? Finally, error checking can be performed on the data in the segment to check if the segment was changed during transmission. So the error control thing, right? Right. So next is the network layer. Now, the transport layer was basically concerned with the process, right? So it has a process A, it has a process B in the destinations. It just says that, dude, I need to get this thing to that process. That's it. It doesn't know anything. It doesn't know where that is. It doesn't know how long it will take. It's just that it knows that I need to reach that certain process, right? So next comes the network layer, which takes information from transport layer and then it sends off to the data link layer on the sender side, the usual. So network layer here, the PDU is called packet. Like finally, it's called packet, right? It's actually called packet. Both the formal and informal name of this layer is packet. Anyway, so this layer is responsible for the delivery of individual packets from the source host to the destination host. Now, what it means is it actually is bothered about how to reach this packet from this source machine to that destination machine, but it does not concern about what type of packet is it carrying or what process is this packet about, right? So in this layer there is a protocol which is called the internet protocol, IP, as you have all heard before, I guess. So it has primarily two functions. It adds an address to identify the sender and the receiver host and decides which path to take, which is called routing. Now this IP basically is what to say, this IP is used to identify all the names. So in this real world, we have names. In Brac University, we have student ID, and in the internet world, there is the IP, right? So it's a universal address, and it is unique for each host. So in the IP, another name for IP is logical address, which is the title of the slide. Anyway, so this IP address is unique for everything. Now, this is not entirely true. We will know soon why, but for now, for the sake of introductory classes and the slides, we will assume that all the IPs in the world is very unique. Like you and I cannot have the same IP because it is the unique identifier of each device in this world, right? So this IP address is of 32 bits. And this 32 bits is divided into 4 parts. Like each part has 8 bits in it, right? So this 8 bits is all converted into one decimal address. So each of these 8 bits is converted to one decimal number. So if you see the example on line 4, so 192.168.10.1, right? So this each of this decimal number carries 8 bits of bits. All right, so together they make 32 bits. So we will know in great length how this is constructed later. Yeah, so this does not concern any other layers, like independent of underlying physical networks and everything. It does not care how it's going. It just knows that I'm here and I need to go to that certain destination and how it will go, like the destination route, right? Like Uber. Now here in the network layer, what it happens is either each device is has an IP address, so it's not like only the end devices will have IP address. The intermediary device will have the IP addresses as well. All the devices has IP addresses in simple terms, right? So there's A, B, C, D, E, and then the two end devices that we're going to deliver the packet from. So from A, it will go to F. So A creates a packet and then it goes to F. Now the fact that from B it took the route below is the work of the network layer. In this router, it decided which path to take, the path in the top or at the bottom. So each router has a table of addresses, and from that table it looks up that address and decides to which route it should take, right? So these routers, so you know that there are 7 layers, right? But in the routers they only traverse the bottom 3 layers, right? It does not need to know what process it uses. It does not need to decode the application and whatnot. The application and the process is only for the two end devices. So as you can see in the below figure, that from here, if I were to mark this, so it goes here, then to B, and then it goes only up till the network layer, right? And then it goes down again, and the whole thing is repeated, right? Right. Anyway, so there's another example. So there are 3 LANs now, and there is a sender, there's a connection intermediary devices, and then there's a sender and the receiver at the right. And so sender will send a packet. It comes to the router. Now, as I said, the router needs to decide which path to take, right? So it decides it's the up one or the lower one. It looks at the routing table and then selects the table, the route at the bottom, and sends the packet to the next router. The process is repeated. Like which path? It selects the next one. So then it goes there and the same thing, right? All right. So next, the data link layer, the second last layer of the OSI model. So in this layer, what it happens is it adds a header and a trailer. So on all the previous layers, there's only header and there's only header, right? There's no trailer. So in this layer, there's header and trailer, and it's called framing. Anyway, so data link layer here, the PD is called a frame, and it's responsible for moving frames from one hop to the next hop, right? All right. So if I were to go the functions, sorry, I messed up a little. So the functions of this layer is framing, physical addressing, flow control, error control, and access control. So kind of like the some similar things with the transport layer, but yeah. So in this layer, what it does is basically identifies to which direction take on each hop. So in this whole figure, each device is, each intermediary device, each end device is a hop, right? So network layer, it might be a bit confusing. The network layer is concerned only with the delivery from the source to destination and to identify which route to take. It does not know how to reach to that next hop, right? It need to there has to be something else to point the packet to where to go to next, like where to go, where to jump, right? So the fact that the packet is delivered from A to B is the work of say, what is this, data link layer, but the network layer is concerned from A to F, not A to B. So if I have to give an example, the network layer says at A, it's like, in the network layer at A, it's like, I need to go to F, where do I go? And from A, it gets a signal that it needs to go to B. The signal, the fact that it gets the signal that it needs to go to B is the work of data link layer. So the packet comes to B, right? So here at B, again, the network layer is like, I need to go to F, where do I go? And the router says, go through that link. And then the data link comes in and says, to go to that link, you need to go here. So which is E, right? So the next layer will be like, come to E. So it goes to E, and network layer is like, where is F? And then E is like, you need to go that way. And data link will be data link layer would be like, hold on, I'll identify the next hop that will go to F, right? Yeah. So there is a physical address. In this layer, there is a physical address. So in the transport layer, there is the port address. In the network layer, there is a logical address. Now in the data link layer, it uses the physical address to identify each hop, right? So it's also known as MAC, media access control, and this thing is about 48 bits long, and it's represented by 12 hexadecimal digits grouped in pairs and separated by hyphen or colon. So each of this number is a hexadecimal, and each of this hex digit is of 4 bits. All right. Okay. Then there's the physical layer, the layer that actually carries the data over to the next devices, right? So the physical layer is responsible for movements of individual bits from one hop to another. Functions are physical characteristics of interfaces and medium, like these ports and these lines and whatever, representation of bits. So it carries the bits. It controls the data rate at which speed the data is carried, and synchronization of bits. Like there has to be a synchronization between the sender and the receiver of the devices, or else they will be out of sync. All right. So there are physical topologies like the bus or the ring. So this one is called the ring. There is the hub. There is a lot of things. Then there's the transmission mode, simplex, half duplex, full duplex. So half duplex is like one-way communication, and full duplex is both-way communication, right? So half duplex is like a walkie-talkie, and full duplex is like when you're talking over a phone. Now, there is not much in the physical layer, and that's it about the OSI model. So here you have all the summary of all the layers, and that's about it. See you in the next lecture. Bye.